Hi everyone and welcome to my new video. Today we are here to talk about black holes. This is the second lesson about this beautiful topic. Yeah. So sorry. I can write. Okay. Oh. uh, Okay. So before recording this video, I was watching a beautiful film about Stephen Hawking life, theory of everything. Yeah, it's beautiful. It's beautiful, that film, and anyway, today we are going to talk about black holes. Um, Motion of a particle in a Schwarzschild spacetime. Okay, in the last lesson we saw which is Schwarzschild metric. So which is Schwarzschild metric? Schwarzschild. Okay, it's a strange and difficult name. So Schwarzschild metric is the S square is equal to. Oh, it's raining here. Huh. It's bad today, weather. Anyway, r square sine square theta dphi square. Oh no, it was a sound, a particular sound, a bad sound. It wasn't. It wasn't raining. Yeah, plus theta square. Okay. We have this metric. I remember you that a metric. We need a metric to describe our space. Okay, the square equal to g mu dx mu for dx nu, and I mean this is the x mu square, okay, and g mu is a tensor called metric tensor. I talked about this topic in my channel, metric tensor and metric in general, and so the x mu square, thanks to Einstein convention, we can write, of course, the x mu for the x nu, where nu and nu is equal to 0, 1, 2, sorry, 2 and 3. Okay, because g mu nu is equal to 0 for, oh my god, for mu nu, mu different by nu. Okay. This is some general metric in a general Riemann space. Now, in Minkowski space, space-time, in theory of special relativity, we have the square is equal to minus c t square plus t square plus. Okay, we have these. And g mu is equal to minus 1, 1, 1, 1, and other components are 0. Now, Schwarzschild metric is particular because it describes a particular kind of spacetime, a central symmetrical spacetime. A central symmetrical spacetime is a spacetime where, if I have this place, okay, and we have a point over the surface. Okay, this is a surface. We have a point over this surface, or we have a infinity points over this surface, and there is a distance r between the center, okay, between the center of gravitational field and the point. Every point over this surface has the same distance r, okay, and this distance can be a metric, okay. So a metric of this kind is called central symmetrical metric, and Schwarzschild metric is a central symmetrical metric, but we suppose that there isn't any mass and energy in our spacetime too, okay. Now, now we have our space-time, okay. So space-time, and at the center of this space-time we have a corp with mass and prime. This corp now we can describe space-time thanks to a metric called the Schwarzschild metric, okay? Because this corp sees the space-time empty, okay? But there is a corp, another corp with mass m, and this corp can move in the space-time, in this space-time, in this Schwarzschild, okay? Schwarzschild space-time. This corp can move in the space-time, so, and we can describe this motion of this particle, of this corp, okay, and which is the equation that can describe the motion of a particle in a Schwarzschild spacetime, a spacetime described by a Schwarzschild metric. We can use two different equations, two different ways. The first way is using geodetic equation. We find again this equation because it's too important in theory of general relativity. So plus this, okay. Sorry. It's equal to 0. Where the s is equal to Untime. Sorry. The S is Untime of a corp. So, for example, I see a corp and I measure his time. He measures his own time, the S, different by me time, different by my time, okay? And the S is so on time, and light with mass equal to 0 can't have an own time, the S, okay? And so I use another parameter, the lambda. So in this lesson we are going to describe a motion of a particle in a Schwarzschild metric, but this particle can be a photon or an electron, okay? Of course, we we don't study quantum effects on the on this particle. This particle can be a corp, okay? So we have a corp. This corp can be me, and this corp can be light too, okay? In case of light, we have a different case because light haven't got a mass, haven't got any mass, and so we could use this parameter, but we don't use geodetic equation to find this motion, but we use Hamilton Jacobi equation. In my channel, in my YouTube channel, I done a course about canonic formalism, where I explain Hamiltonian function and Poisson and so on, Maupertuis theorem, Liouville theorem, but I didn't talk about Hamilton Jacobi equation. Why? Because it's very easy, this equation, very. We saw this function, the Hamiltonian function, and is equal to minus derivative with respect to time of function, okay, of a particle, q, t, okay. And this equation is Hamilton-Jacobi equation, but this is a principle, okay, a basic principle of canonic formalism, but it's very important the meaning of this equation, okay, and it was a mistake. This was a mistake. Yeah. I had to talk about this topic. Anyway, we have this equation called Hamilton-Jacobi equation, but in general relativity, I have to write this equation in another way because we have that p mu for p mu is equal to m squared. Oh, I can't write it here. M square c square, and p mu is equal to derivative with respect to x mu of action, mind, sorry. Okay, thanks to these informations, we can write Hamilton Jacobi equation in general relativity in another way, and this way is g mu nu. Sorry, I write red. Okay, g mu nu. Okay. Perfect. My m square c square is equal to 0. This equation can say can describe the motion of this corp, okay? But in which way? What else? Okay. What else we have to know to find this motion? Okay, we are in a Schwarzschild spacetime, so the metric tensor is a particular form, and this form is I don't know if we could write oh if you I should write, yeah, I should write, which is tensor metric tensor g mu is equal to, so Gimino with mu and nu different by them are 0, and other components are, we have here, okay, sorry, Firstly, G001 minus RG on R. I forgot it. RG is a Schwarzschild ray. Um, you you should watch my video before to watch this video. Okay, the first video, the first video about this topic. Okay. RG is Schwarzschild ray and is equal to minus 2 gm prime on c square. Okay. Okay, remember this, please. Okay, and so G00 is equal to this, and G11 is equal to 1 of 1 on 1 minus and so on, and G22 is equal to d theta square, and G33 is equal to sine square theta. Okay, d phi square. Okay, sorry, G22 is equal to minus r square. Okay, so d theta square c dt square minus d square are spheric coordinates. Okay. Anyway, we have other components: G00, G11, G22, and G33. Perfect. Now, thanks to these components, we can write Hamilton Jacobi equation in this way. Sorry. Y square for the same topic, okay? Because we have Einstein convention, a quadrivector, a four vector x mu square. We can write these such as x mu x nu, okay? And so here we have x mu for x nu, and here we can write the square, okay? Mine. Perfect. Okay, and oh. Okay, this is the equation. Now we'll look for a solution, a particular kind of solution. We can write this solution of the function such as minus energy 0t, okay, plus n phi, okay, plus srr. Okay, where SRR is the radial part of action, and m is angular momentum, and E0 is energy. Perfect. We have these. Three variable, G, phi, and R. Theta, there isn't theta. Because why? Because I forgot to say, I think, maybe the most important thing in this lesson, because we should suppose a plane where this particle, this corp, can move free. Oh yeah, and this plane is, for example, theta is equal to pi on 2, okay? Because yeah, we can suppose a motion in this Schwarzschild spacetime, ma this motion must be a central symmetrical motion too. Okay. I mean, we have the center of this gravitational field, and we have plane, okay? And we can choose the plane theta is equal to pi on 2, okay? And so we have that the term with theta is equal to 0, and so we have just t, phi, and r, the best. Right there, pi and 2. And so, of course, the solution S must be with just t, phi, and r. Okay, and it mustn't have a term with theta, because the term with theta in the equation is equal to 0 too. Anyway, getting this term in this equation, we find the derivative with respect to r of radial part of action, and so we can find radial part of action in this way. R is equal to integral of energy 0 square on c square. Yeah, it's too long, so I should do this. Okay. In this way, SR is equal to integral of what? Energy 0 square on c square. Sorry. For this, m square c square. Sorry. M square c square plus. Oh, I remember you. There is a Telegram group where you can join and talk about everything you want with me and with other people, and you can fun. It's fun. This group is very fun. And so I remember you this. If you wanna join, you're free to join, and you make me happy. So anyway, plus m square r square. But I am already happy, thanks to God. Okay, but if you wanna join, you are free to join. Okay, RGR. Okay, this expression, we can find these thanks to we can find this getting this term here, and we find the radial part of action. Now, what shall we do? What shall we do now? Uh, we know that the derivative of action with respect to energy, I call this energy zero, the relativistic energy. Energy zero is, and of course, is energy of a corp, okay, and energy prime is while it's the energy of corp that makes gravitational field. Okay, so this derivative is equal to constant. And thanks to this, we can find C for T. And this is equal to, and this is equal to energy zero on mc square of integral the r of what? 1 minus rg on r. Sorry. Energy zero on mc square minus 1 plus m square c square r square. Oh, it's too long. 1 and 2. Okay, so we found a particular term, and this term is time. Okay, and now we know that derivative with respect to angular momentum is equal to constant 2. And so we can find phi. And phi is right the path of this particle, the path of this corp. Okay, this corp that it moves free in the space time. Not free. This corp it isn't free because it, it moves thanks to gravity, and gravity is a force. For Newton, according to Newton's theory, gravity is a force. Well, what did I say? No. Anyway, gravity make it move in the space time. Makes it move in the space time. So it isn't right free, but anyway, so phi is the path of this particle of this corp, and is integral. Sorry for this terrible integral. Phi is equal to integral of m r square energy zero square c square mc square plus m square r square 1 rgr. Okay. Oh, I remember you that at 6 o'clock p.m. there will be a live where I speak Italian, yeah, and I explain some topics randomly, and if you wanna join this live too, you are free to do these too. Okay. Anyway, this is path. This is the equation to find the path of a particle, of this particle with mass m, energy 0, and so on. Phi. Yeah, phi. Okay. Now, this is a particular kind of integral in mathematics, but I don't want to say his name because I don't know how um, to say this word in integral. So, for Italian people, this integral is called integrale ellittico, but I don't know how to say this word in English, so I so let's go on. Okay, now we found our uh, com- we found this path, this this way of particle. Okay, phi, and phi is path of this corp in Schwarzschild space-time. But an application of this motion of a corp in this space-time is the motion of a planet in on orbit, okay, because there is a particular phenomena called precession of perihelio of orbita of a planet. It's a long name, but it wanna say this. So we have a planet, its orbita, and so this is, for example, Earth. Okay, okay. So sorry, one moment, please. Okay, wait. Okay. So this is Earth. Okay, and we have a point called over this orbit called perihelio. Okay, perihelio is the most near point. Is the most near point to what? Is the most next point. It's next to sun. Okay. Okay, and this, so it's called perihelio. Perihelio. Okay, I don't write this. Anyway, when Earth arrives here near perihelio, so this is sun. Earth is more big of sun than sun. Earth is more big than sun. This is beautiful. Okay, yeah. This is the sun. Okay, perfect. Too big, maybe too big. Okay, now, now when Earth arrives near this point, perihelion, orbit starts turning around this point. These things. So orbit starts turning around per helio in this way. Okay. So after we will have a new orbit where Earth can be moved, and when arrives again near the perihelio, he turns again around perihelio. Another time, another time, another time, another time, another time, another time, and then heal it it back uh, in the original position. But this is this is a bit wrong because it's a bit wrong because um, uh, this isn't the real life. Okay. So now, how to describe this phenomena, this precision of perihelio?